High voltage vacuum interrupter. High voltage vacuum interrupter is a switch that is used to disconnect mains under load. During this process, the arc usually appears. Metal shields between the ceramic blocks of the interrupter body protect the insulator from the metal vapor disposition during the arcing process. But these shields also influence the electric field distribution and may decrease the dielectric strength of the device. So a detailed analysis of the electric field distribution is required. Interrupter features rotational symmetry, so I'm going to simulate a two-dimensional axisymmetric model. Interrupter operates at AC voltage, but I'm going to simulate the worst case scenario when the voltage is maximum. So I'm going to simulate electrostatic problem. Okay, let's start QuickField now. In QuickField I create new problem. Interrupter. Next. Problem type is electrostatic. Interrupter features rotational symmetry, so the model class is axisymmetric. Length you need some millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here using QuickField instruments, but I have already the model prepared in the CAD system, so I'm going to import the model from the AutoCAD DXF file. Here is the file, and here is the model. Here you can recognize vacuum chamber, grounded electrode, high voltage electrode, insulator. In axisymmetric problems, the axis of rotation is a horizontal one. So I switch to insert mode and draw the axis of rotation, and I should remove all objects located below the axis. Switch to select objects mode, select with the rubber band and remove all objects below the axis. Okay. In fact, the electric field is distributed not only inside the interrupter, but also in the air outside. QuickField cannot calculate the field distribution in the infinitely large space, so I need to limit the simulation domain. Again, switch to insert mode, change the line type to the half arc, and draw the air block boundary. And I move this vertex to the left. Okay. The geometry model is ready. Now let's assign labels. Through labels you can explain the geometric object's meaning and provide physical properties. Switch to select mode, click the object to select and type in the label name here. This block is air. This block is vacuum. Let's zoom in. Select mode. These blocks are insulator. Hold the Ctrl button pressed to select multiple objects at the same time. And other blocks are conductors. There is no electric field inside conductors, so I do not assign label to the bodies. But I'm going to assign label to the edges, to the surfaces of the conductors, and specify electric potential. Okay, I will select this way. Now you see the block, the edge, and the vertices are selected. I'm going to assign label only to the edge. This is the grounded electrode, so for the edge I assign label grounded. And these edges belong to the high voltage electrode. I assign label high voltage. These are also metal edges, but they are not connected to the voltage source. They are floating. So I assign to them label floating 1, floating 2, and this would be floating 3. Okay. Now let's provide physical properties for these labels. Double-click the label name in the tree. Electric permittivity of the air is 1. Electric permittivity of vacuum is 1. And for the insulator, it is 9. Grounded electrode has 0 electric potential. High voltage electrode electric potential is 325 kilovolts. And floating electrodes has unknown potential. They are just floating conductors. So for the floating electrodes, I specify floating conductor boundary condition. Now the material properties are ready. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. The problem is solved. Let's take a look at the results. Here you can see the electric potential distribution. Let's zoom in. Grounded electrode, high voltage electrode, and these are floating conductors. You can change the presentation type and switch, for example, the color map of the electric field strength. So using the color map, you can find the most stressed part. And if you hover the color picture, here at the bottom at the status bar, you can see the electric field stress value. You can also use the local values tool, click any point and get the exact number of electric field strength and electric potential in this point. You can also use the contour tool and build the contour the same way you build the edges in the geometry model and get the field distribution along the contour on the XY plot and the exact values you can see in the table. Coordinates, electric potential, electric field strength. Here you can change the tabulating step and get more detailed results. So this way, using the two-dimensional axisymmetric model, we were able to calculate electric field distribution in the vacuum interrupter, and now you can easily check the electric field stress value in any part. If you search for the vacuum interrupter on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.